Good afternoon, everyone. It is my great pleasure to welcome and introduce to all of you Professor Vishal Mishra from Columbia University, where he is a professor and also a recently minted Dean of Vices in Computing, or I mean Vice Dean of Computing, of AI and Computing and Data Science. He is also a well-known expert in the field of analysis and modeling of complex networked systems, and is well known for many contributions in networking and systems, and also for his work on net neutrality. He's also one of the founders of Cricinfo, which is the world's largest cricket site, acquired by ESPN. And on a personal note, were it not for Cricinfo over the last many years, almost decades, I might have written a few more papers, but have been infinitely less happy. So with that introduction, over to you, Vishal, who's going to tell us today about some really interesting new work on understanding how large language models work.
Like Professor Sid Dalal in the Statistics Department at Columbia. And as I just said before we unmuted Zoom, this is the first time I'm giving this talk, so I don't know how it'll go, but let's see. So, given the topic, a talk on LLMs, you must be assuming that I'm a researcher in NLP. No. At least deep learning, large language models. I have to be at least an expert in machine learning. Give me something, right? Unfortunately, no. Yeah, I'm just a cricketer. That's what Hari said. This is actually a photograph not far from here. It's in Belmont. So I used to play the Mass State Cricket League, and this is a few miles from here. But I jest, cricket has something to do with the talk, and I'll explain what. So the origins is that, as Hari mentioned earlier, I co-founded this cricket portal called Cricinfo in the early 90s. Cricket is a very stat-rich sport. Think baseball, multiply that by 1,000. So what we had done is we had created a free online stats database called StatsGuru, which has been available since 2000 on Cricinfo. And querying this database is done through web forms. And ESPN acquired the portal in 2007, I think, yeah, that's it. Yeah. And they kept the query interface. This is what the interface looks like. So as you can imagine, hardly anyone uses StatsGuru. Although you can use it to, well, some people, some crazy nerds do it. I'm one of them. But most people don't use it because this interface is terrible. It's daunting. To do the easiest thing, you have to go through this, even to get to the screen, you have to do a search on another screen. And I'm still friendly with the people who run Cricinfo at ESPN. So the chief editor, whenever he comes to New York, we meet up, and I keep telling him, or I kept telling him, why don't you do something about StatsGuru? At least build a mobile interface in the UI. And he was here the January before the pandemic started. And I again told him, why don't you do something about StatsGuru? And he said, why don't you do something about StatsGuru? So GPT-3 was released in early version in July of 2020. And when it got released, I saw somebody tweet out this thing where he was using GPT-3 to write SQL queries that worked on his database. And I thought maybe I could use that to create a natural language interface for StatsGuru. So in the process of doing, I think I accidentally invented what's called RAG now, Retrieval Augmented Generation. And using that and in-context learning, I was able to create this front-end, natural language front-end for the StatsGuru database. Now, mind you, I had no access to internal GPT-3 weights, and GPT-3 had no idea what StatsGuru was. But still using this, RAG and in-context learning, we were able to develop this natural language interface. We developed a product called AskCricinfo, which has been running on ESPN since September 2021. Hari actually was following the development before it got released. And now this interface changed from this. Now, the same query which you see here, you can ask in natural language. Virat Kohli's record against leg spinners in IPL since 2017, something like that. What we do is we take this query, get its intent, convert it into our own DSL, send it to GPT-3. GPT-3 writes it out, and then we get the actual answer and get it and displayed. So this has been running since September 2021. But I remain mystified, we got it to work, but why does it work? How does it work? Because in context learning, as I said, GPT-3 had no idea what stats guru looked like. I had no access to internal GPT-3 weights. Still, it worked. It was learning in real time, something that had no idea about. And so people have been trying to explain this thing called in-context learning, which is, you show GPT-3 or these large language models few examples and it'll learn in real time. So it has changed the time scale of learning. You don't need to go and retrain your weights and go through that whole process. You can teach this dog new tricks. Now, there have been some attempts to explain this in-context learning, where there have been some papers where they train these language models, the same architecture, to solve linear programming problems, and then they show new linear programming problems and it learns how to solve them. Somehow that seemed unsatisfying because these models are not solving linear programs, right? They're generating text. So how does it work? So I stared at the transformer architecture for hours. It didn't help. I have no idea how it works and why it's able to learn in real time. On top of it, now recently there have been lots of papers with different architectures. There's something called Mamba. People have shown RNNs, LSTMs that show the same behavior of doing in-context learning. So probably whatever the mystery is, it's not here. Attention maybe is not all you need. It's something else. So now, after getting frustrated, I said, how does it work? We started to sort of build a first principles model for LLMs to explain in-context learning. And this talk is about what that model looks like. So, the roadmap for the rest of the talk. So what I'm going to focus is on the training objective of LLMs. I think that is the key, which is predict the next token. So we'll interpret the text generation process as approximating a very large matrix of multinomial distributions. We have a universal representation theorem of multinomial distributions as a linear combination of basis distribution Dirichlet. That's not important what it is, but we'll use it to show how these LLMs work. And what really is happening with these LLMs is the prompts that you give, they serve as new evidence or in sort of a Bayesian learning process. So when you give a prompt, what at a very high level, the rest of the talk, I'll try to show that. If you give a prompt, what it'll first do is it'll try to locate something which was in the training set close to the prompt, a distribution corresponding to that. And then it uses the prompt as new evidence. And then it'll compute a posterior using this new evidence and whatever was a pre-trained model. And this posterior distribution is used to generate the new text. And that's how it's able to learn in real time. So that's the message. So if you want to leave, you can leave. I'll just try and spend the rest of the talk explaining or showing how that works. Okay, so we all know about ChatGPT and how it's so popular and it hit the world changed in one day. Yeah.
Sorry, I just have a question from someone who's not used to most of the terminology you were just using.
Yeah.
Is there some important practical question that you can answer better now?
Yeah.
It's going to be a punchline that comes later.
Yeah, there is actually several important practical questions. First of all, how does this work? And then it tells you what to focus on. And we have a paper, it's on arXiv. We also show how you can improve the generation process so we can reduce hallucinations, and what is sort of a better way to train these systems. There are also, we think that it opens up a whole new line of research and a way of looking at these LLMs. Okay, so what is the training objective of these LLMs? So it's predict the next word in a sequence. So when you give a prompt to these LLMs, something like the cat sat on the, then what it does is it has a vocabulary. All these models have a vocabulary of tokens. What they do is they produce a distribution over the vocabulary. So when you say the cat sat on the, then it'll produce this distribution where mat will have a high probability, couch will have a high probability, and courage, very low probability. Probably somebody wrote a poem, the cat sat on the courage, or who knows. The cat sat on the, maybe there was some typo somewhere. So these things will have low probabilities, but mat and couch, those are sort of the obvious terms that follow the cat sat on the. And so once it has generated this distribution, what these LLMs do is they sample from this distribution according to this probability. And after that sampling, they pick a token, append it to the text, and this process keeps on repeating. And through this training objective, was it? No. Okay. So these models learn a lot of these things simply through this training objective. So it'll learn that the probability of the cat sat on the mat is higher than the cat sats on the mat. So it learns grammar implicitly, not explicitly, just it learns these probabilities. The cat sat on the mat, the probability is higher than the whale sat on the mat. So it's building some sort of a world knowledge, again, through training, through looking at these tokens, through predicting the next token, and just computing these probabilities. Arithmetic, 2 plus 2 equals 4 is greater than 2 plus 2 equals 5. The probability. It has no idea what these numbers are. It has just seen this pattern more than the other pattern. So, when people say it's developing a world model and all that, it's simply developing, these probabilities through training. Now, one of the very surprising things that happened with these LLMs was this thing of in-context learning. So what is in-context learning? So zero-shot learning is when you give it a prompt and you expect an answer without any sort of showing it examples. So for instance, what I'm saying in blue, what is the sentiment of this review? This movie is boring. I've not given it any examples, and it'll say negative without it, showing it anything. In context learning is I show it some examples. What is the sentiment of this review? I like the movie, positive. Horrible movie, negative. Now I ask, this movie is boring. Now it'll complete it to say negative. I've shown it a few examples, right? So this is the example. This is an example of in-context learning, where you show it a few examples of what you wanted to do, give it a new sort of task, and according to the example that you've shown, it'll complete the task. Now, there are different kinds of examples of in-context learning. There is what's called regular in-context learning, where it's doing what is expected, right? So the examples that you show is something natural, something which is negative. In the example you show it's negative, something which is positive, in the example you show positive, and then it learns. So that you kind of expect these language models to know. There's something called flip label in-context learning, where you simply flip the labels of what you want to be called negative. Now you'll call it positive. What we expect to be called positive, we'll call negative. And it learns that. The third sort of most difficult of these in-context learning examples is semantically unrelated label in-context learning, where the example that you show has nothing to do with, let's say, the prompt. Right? So here contains no wit. I call it foo, very good viewing, bar. Nothing to do with, but it still learns. Again, with a few examples, it learns. And this thing emerged with very large models. GPT-3 was the first time people observed this phenomena of in-context learning. In fact, the title of the GPT-3 paper is something like GPT-3 model, GPT-3 is a few shot learner, or something like that. That's when, when very large models happened, this property emerged. So let's try to understand how it works. And again, I'll go to the AskCricinfo, for example, to kind of show what's going. Yeah. Yeah.
Are all three of those going to result in something that does the task correctly?
Yeah, all.
So like, it's not like for the second one, is it going to say the flip label?
It is going to say, yeah. So you can.
It's going to say the truth.
No, it's going to say the flip. So you can teach it all kinds of tasks. Something which is expected, something which is opposite of the expected, just one minus. You kind of think that, okay, maybe that's also not too difficult to teach. And then something which is completely unrelated, but it learns even that. Yeah, you can say that, as long as you show the right examples. Yeah. Okay. So what I'm going to do is I'm going to walk through, the product that we built, AskCricinfo, how it works, and develop an intuition of what's happening. So what we did was we created our own DSL, domain-specific language or meta language, to interpret query intent. So if you have a query, natural language query, which says, what are the best bowling figures in an IPL final? Now, IPL is one cricket league, like the NFL or, like a football league. So there are several leagues around the world. IPL is the Indian version. So you take that query, then you adjust it a little bit, and you replace IPL with an inert name like Tournament 0. So that the same query can work for multiple different kinds of tournaments or leagues. All you need to do is at the end replace Tournament 0 with IPL or BBL or whatever tournament that you're looking for. And then you convert that into this meta language, which is you can interpret it programmatically and rewrite it as a REST API call or a SQL query call or whatever you want to do. But once you have reached this format, then you can sort of mechanically go from here to get the query. So the interesting step is going from what are the best bowling figures in an IPL final to this meta language. Okay. So now let's see what happens when we test this thing on ChatGPT. So I have given it a query of what is Mohammad Siraj is a bowler who plays for India. Mohammad Siraj's best bowling figures in ODIs. ODIs are a form of game. And the answer generated by ChatGPT, I've listed it there, is I've color coded the answer. The color is according to the probability which was generated for that word or that token. So green is the highest probability, red is the lowest probability. So if you see the answer that is generated, Mohammad Siraj is repeating the name, high probability, of course. You've asked a question about this person, it's going to repeat. Mohammad Siraj's best bowling figures in ODIs, so far is just repeating the question, rephrasing the question as an answer. Everything is high probability. Then it comes to the figures, 4 for 48. Now it's making things up. You can see that they are low probability. They're reasonable figures in a cricket game, but they are not his best figures. They're completely unrelated and it's low probability. So it does that, and then it keeps on generating, which he achieved against. Now I see new is low probability, because who do you play against? There are several choices. New Zealand, Australia, West Indies, Pakistan, Bangladesh, blah, blah. Out of them, it picked new. It sampled new from that distribution. But once it got new, the only thing that can follow new is Zealand. Then it again became high probability. Right. Now it says in January 2020, again made up. The answer is completely made up. When ChatGPT came out, because I'd been working on it, several people asked me, what is this? Everyone was very excited about it. And I said, the analogy that the mental model that you should have in your mind is that it is the most helpful and knowledgeable entity you can ever encounter, but with early onset dementia. It's going to confidently make things up. You have no idea. It has no idea when it's making things up. It's living in some alternate reality. So you cannot trust what it's saying. Right? So it has made this answer completely when I asked the question. The answer looks very plausible. Right? If you ask Hari, this is a very reasonable answer to give. Somebody probably has best figures that look like this, but this is not the right answer. Now, I give the same query in my meta language format. What is person zero best bowling figures in tournament zero? Again, made up answer, but the answer is in English resembling the query. It is not in meta language because GPT-3 has no idea what the meta language is at this point. Now what I'm going to do is I'm going to show that same query with 8 related examples as a prefix to the query. So here I've shown it these 8 related examples, and now it has nailed it. After I show it these 8 examples, it has gotten the meta language absolutely right, and it completes my query by giving the right meta language. What is person zero best bowling figures in tournament zero? The first token should be bowler. The probability of that is 100%. So by showing these examples in real time, it has learned. And we just saw that if you don't show the examples, it's off in its own world. But now, in real time, it has learned what the meta language is. Okay. And let's go these are the related examples. This is a new query. LLM response, completely right. Yeah.
What made you decide to use a new query language instead of SQL?
So, well, first of all, there are some practical reasons. We wanted to generate a REST call. That was the interface to the. Secondly, if you go back, the internal database, there are 3 different databases. I shouldn't be revealing too much, but the internal database is very complicated. You could generate SQL. In fact, we are able to generate SQL. This architecture lets you generate anything: SQL, NoSQL, Python, your own DSL.
But you don't generally need to give your own examples to get good SQL.
No, but if you're giving it to a new table that it has no idea what the columns are, what the terms mean. Generally, right?
SQL schema does a good job.
It does a reasonable job, but for a new language, it doesn't. And so suppose my database has 500 tables, 2,000 columns. There's no way you can dump all of that in the context. Right?
That makes it free.
So we'll come to that, how these things work. Yeah. So yeah, now you do that and you get the right answer. Hari can verify that, yeah, these are his best figures, right? You don't you remember he took 6 wickets? Yeah. So what happens is it's learning the meta language along the way. Now what I'm showing is at this point, it has seen only the first example, only the query part, not the meta language. At this point, the probability of the right token is extremely low. It's, in percentages, it's 0.27%. The highest probability is, person. It's trying to repeat person zero. So at this point, it has no idea about what the meta language is. You show it some more of the query and the meta language, it still doesn't really know. It should have said group by, but the group by probability is close to 0. Now, after 3 examples, it has picked it up. Now the probability of the right token is 0.98. You go further, the probability becomes even higher. And by the time you're here, it has learned it almost perfectly. So what's happening? So let's do a quick LLM primer. What kind of parameters exist, both in terms of how they work internally and what are the external parameters. So, we can think of LLMs having 4 different kinds of parameters. One is the vocabulary of the LLM. How many words or tokens it knows about. So that's the dictionary of the LLM. That's what it can generate. Then is the context size, which is the memory or size of the prompt that the LLM responds to. Right? So every, we hear Opus has, context size of 1 million or whatever. That's the memory of the LLM that it'll respond to. Parameter count is roughly the weights of the neural net. We heard GPT-3 had 175 billion parameters, GPT-4 rumored to have 1 trillion parameters, and so on and so forth. So that's the parameter count. And the embedding vector. So this is a vector which is used to represent words and tokens, and the vector has a certain size. So if you take, let's say, ChatGPT, the token size, the dictionary is roughly 50,000, the first version. The context size for 3.5 is 8,192 tokens. The parameter count of the largest model, Da Vinci, is 175 billion. For GPT-4, we don't know, but it's rumored to have 1 trillion parameters. And the embedding vector size originally was 12,880. Recently, another version has 1,536. And even more recently, they've released this new Matryoshka-based embedding, which is even smaller. But that's the size of the vector that is used to represent each token internally. So this is a question that I've asked. Do you know who created the first generative text model? I showed the answer. It's actually Shannon in his 1948 paper, the paper that introduced information theory. He has a section where he has this generative text model, which is basically a first order Markov process where he has transition probabilities between words. And he's just generating words according to that just first order Markov process. And the text that is generated just from this first order Markov process, it looks reasonable. It's almost close to English. I encourage you to go back to the paper, look on page 7. It's really interesting reading how he sort of step-by-step develops this model. But he had only, computationally, he could only compute first order probabilities. LLMs are basically nth order Markov chains, where n is the context size, the prompt length. So based on that, they are computing the transition probability. So now let's go through this exercise of imagining text in the real world. So imagine you have a corpus of the entire text of the world, and every token or every word occurs with a certain probability. So assume we're trying to generate text, and the first word, let's say we pick protein. Now every word occurs with some probability. Let's say we pick protein. Now, given that protein is the first word, there will be a multinomial distribution for the next words. It's going to be sparse. Most words do not follow protein. Right? 2 words that might follow are synthesis or shake. Right? So you can sample from synthesis or shake. Suppose you pick synthesis, then again there'll be a sparse multinomial distribution over the dictionary, but that'll be dominated by biology terms. If instead you pick shake, then it'll be generated by gym and exercise and those kinds of terms. So, the distribution changes based on what word you picked after protein. So now what you can do is you can imagine this represented in this huge probability matrix, which has 50,000 columns. So that's the size of the dictionary. Each row corresponds to a prompt. So each row corresponds to a prompt, and each row has the multinomial distribution corresponding to the prompt, or what the probability of the next word is. Now, the number of rows of this matrix is 50,000 to the power 8,000, or 8,192, whatever. That's more than the number of atoms across all galaxies. So clearly, even with 175 billion parameters, you cannot represent this matrix. Now, fortunately, the matrix is extremely sparse. Why? Because most rows individually occur with 0 probability. An arbitrary combination of tokens, you're not going to find it in real life. It's kind of related to Shannon's concept of typical sequences. But you can imagine that, most of a random combination of tokens is gibberish. Most rows won't occur. Even rows that occur, the distribution is sparse. So rows that occur with non-zero probability, the columns themselves are sparse. Not all 50,000 will have non-zero values. So it's extremely sparse. But even after that sparsity, it's way beyond 175 billion or 1 trillion. Now, use of embeddings also compresses the representation. I'll come to that. But what, at the end of the day, these LLMs are trying to do is come up with a representation of this matrix. And given a prompt, come up with the right distribution, multinomial distribution, and generate text according to that. So this matrix is really the sort of the core of understanding at an abstract level what these LLMs are trying to do. Every row is a prompt. And now this row could also be my meta language with examples. And it'll have the corresponding distribution for the next token. And what these LLMs are trying to do is come up with an efficient way to represent this matrix. Okay. So now training and generation of LLMs. So the training process consists of LLMs minimizing the multinomial distribution error of each row. Let's say the prompt is cat sat on the mat based on the training data. And we show that if you train it in the limit, what the LLMs will generate is the same as the empirical distribution of your training data. So if your training data is a subset of the whole world, you're going to generate the subset of what you have trained it on. That's the training. In the generation process, what happens is you get a text input from the user, the cat sat on the whatever. You convert that text to an embeddings representation because they're not working with text directly. They work with this embeddings. That embeddings that are fed to the LLM, which will generate a multinomial distribution. You sample from that distribution, pick one token, append that token to your text, print out whatever you have generated so far, and then repeat the process. Keep doing it until you reach end of generation token or whatever. So this at an abstract level is what these LLMs are doing. So I'm not paying attention to the sort of LLM specific architecture, whether it's transformers or Mamba or whatever. At the end of the day, they get an embedding as an input, multinomial distribution is the output. So now we have proven some results in the paper where suppose T is a mapping from an embedding space to the space of multinomial distributions. And if this mapping is convexity preserving in the sense that if T is a mapping, then T of alpha epsilon 1, alpha E1 plus 1 minus alpha E2, that is alpha of T of E1 plus 1 minus alpha of T of E2. This is convexity preserving. Then we say the mapping is continuous. So you can think of this as almost like, a Lipschitz-like property of the mapping from the embedding space to the multinomial distribution space. What it's saying is that if you perturb the embeddings a little bit, your multinomial distribution is going to perturb a little bit. Yeah. It's an equality. Yeah. Actually, there's also an intuition that, if you're picking an embedding with probability alpha and another embedding with probability 1 minus alpha, then in expectation, the distribution, there's linearity of expectation. So it's actually an inequality. And this has also been shown by somebody else for some well-posedness of this mapping. But I'll show you. So informally, what it does is it allows a mapping of the multinomial distribution from unseen embeddings as linear combination of mappings of closest known embeddings. Right? So, when I ask ChatGPT to complete the the prompt that Hari and I are going for dinner tonight too. Now, it has not seen, hopefully not, this in the training data, right? But it'll give a reasonable answer to that. Why? Because in the training data, it has seen something very similar. So there are embeddings which are close to this, and it'll find something which is like a linear combination of what it has seen previously seen, plus one more thing. So it's able to sort of generate text from unknown things based on what it has seen in training. Then we also have this universal representation theorem, which basically says any continuous multinomial distribution, which we have, what these things work with, you can approximate as a mixture of Dirichlet distributions with some parameters and some mixing constant that we can determine. And a special case of a Dirichlet distribution is the beta distribution. Again, I'll come to why I'm going to talk about that. But what this is saying that any multinomial distribution corresponds to some linear combination of Dirichlet distribution. You can think of them as some sort of basis. So the conceptual multinomial distribution generation process of LLMs looks like this. Given a prompt, the cat sat on the, it'll convert it into an embedding. Then from the LLM pre-trained model, using our continuity and the universal representation theorem, it'll find an embedding which is closest to that, some linear combination of what it has been trained on. That is a model that has been trained on. That acts as the approximate prior. And then what it does, it looks at the prior prompt again, and that's the new data, new evidence, or new likelihood. Using a combination of that and this prior, it computes the Bayesian posterior. And that posterior is used to generate the next token. That's how it's able to learn my meta language in real time, because it's using that as a likelihood to update whatever it has learned in the pre-trained model. Yeah.
I think of the embedding as like some abstract kind of embedding, or is it the actual embedding of the language model?
It's the actual embedding. Yeah. But it actually plays an important part. I'll come to it later. The embedding will give us some multinomial distribution. And that's what we're working with in this step. And we're updating that multinomial distribution.
Yeah, I was more asking like whether the embedding is like something we have access to if we had access to the weights of the language model, or if it's like more of an abstract kind of like embedding.
We have access to the embedding there. So now let's go through an exercise. Yeah. Yeah.
So from the prompt, I get embeddings. I put them through my LLM, and it produces this multinomial distribution. That's for a particular token, right?
Next token, yeah.
The next token.
Yeah.
So is that the distribution that you're
No.
calling the prior?
Yeah, that's the prior.
Why is that a prior? Isn't that already conditioned on the
No,
prompt?
no, because you're not using the evidence that's there in the prompt to update it. Because the prompt has its own transitions. Like, the meta language that we designed, it had these new transitions which it had never seen before. But it's still able to learn it.
The thing we're putting through the LLM is the prompt.
No. The prompt is not part of the training data. Right? So whatever it's going to generate as the prior will not have the right next tokens, which we saw, when we just showed the first part, the probabilities were low. So where is it learning this meta language from? Yeah.
I'm just trying to decode this picture. So this picture, the posterior that you have here, it's the result of basically the calculation that the LLM is doing on the embeddings. Like in the when you look at like the internal things that we can see, we don't see this prior directly, right?
No.
We only see the result of the posterior.
We see the result of the posterior, yeah. That's used to generate the next token.
You might get to this, but is there some sort of empirical proof, validation that this model is correct?
So,
As in, like, is there a way to show experimentally that this model is consistent with what is actually happening?
So you can show this is what's happening because it is learning, it is displaying in context learning.
But
Right.
you do it with all sorts of other ways.
So it has never seen, let's say, my meta language before. So it cannot be part of the pre-trained model, but it learns in real time. So some sort of Bayesian-like update is happening. It could be some other mechanism. All we're saying is that it is consistent with Bayesian updating. There could be something else, but Bayesian updating is sort of the optimal way to learn from new data. Yeah.
What is the meaning of the adding from prompt? Like, can you maybe explain?
So likelihood is that it's providing new evidence. There are new transitions there. Like when I asked the query, the first token after that was bowler. So that's a transition from my last to this, given all that has appeared before. So that's a new evidence. So now I'm going to update my transition probability. So let me quickly go back. So that's just a fancy term for new data, new evidence. So I'll give you an example. So when I ask this question, what is person zero best bowling figures in tournament zero? Without using my meta language, it generates this. Person zero best bowling figures in. Now it has seen evidence of, when I ask this question, after tournament zero, after the question ends, it should start generating this meta language.
That's called prompt.
Yeah, all that is part of the prompt. So, and all this, these related examples, this is what you can call the likelihood. This is new data. I'm showing you that this is how transitions are happening in this world. Learn it.
So it's not like some random,
Well, it's showing these examples. So it's updating the probability. Okay, this has happened. Let me update my probability. Earlier, my probability of going from tournament zero to bowler zero was 0.027. But now that I've seen it, I'm going to update it. And by the
what you're saying is that the top half is all pre-trained. This stuff it hasn't seen. It's coming new. Therefore, it must be something
new,
that
yeah.
adjusts whatever the
Yeah.
parameter is. And maybe Bayesian update is a simpler explanation.
It's sort of Occam's razor.
Yeah.
It's the simplest. There could be something else, but it's consistent with Bayesian learning. Some learning is happening because you can see, right? It's learning new stuff, which it has never seen before. And you can try it out. Okay, so let's go through this example and maybe, you'll see more of it. So let's say we have a model where we are dealing with only two labels. Given a prompt, you can have either label A or label B, and in most of our training examples, the label is A. So the probability of A is going to be high. Yeah. So one thing is, could you repeat? Is there a mic there? Or? So okay, can you ask the question again and I'll repeat it. So this time maybe I'll understand it. A posterior of what? Without the prompt, there's no posterior, right? So the transformer has learned something, right? But when I showed it my meta language, that's something that it had not learned. So here, I'm going to show you a toy model and what happens there in the toy model. That's exactly what I'm going to do. So in this model, we have two labels. So given a prompt, I have label A and label B. Okay. And I assume that most of the training data, the label for this prompt was A. And I'm assuming that the distribution, the prior distribution of these labels is a beta distribution with parameters alpha A and beta B. And if the training data is primarily label A with rare occurrence of B, then we'll have alpha A is much higher than beta B. Okay. Now what I'm going to do is I'm going to, using this prior, show it examples where the label is B, which is not part of the training data. Okay. So now I'll show it n prompts where the label is going to be B and not A. And if you do that, then taking the beta distribution, which is a form of a Dirichlet distribution. So if you show it for this, then there's a lot of sort of work, but you can show it that it holds for any multinomial distribution. So we're sticking with a simple example to explain the concept. So if you do that, then the updated posterior probabilities for PA and PB are given by those equations, given what alpha A is and how many samples you show. So now we're looking at two different examples. So where the first column is the probability of A, second column is the probability of B for two different parameter sets. Okay. In both, the prior probability from the training data is 0.968 for A and 0.032 for B. So, if you show it that prompt, it's going to say A. But now what we do is we keep showing it examples where the label is B. So after we show it in the top case, after one example, the probability has fallen for A from 0.96 to 0.22. And after three examples, it has almost completely flipped. Now it has learned after three examples that if I'm shown this prompt, I'm going to give it this label, which is completely unrelated. In my training data, I had no examples of this. Whereas if these alpha A and beta B probabilities are large, so in both these cases, the ratio of alpha and beta is 30, which sort of reflects the occurrence of the labels A versus B in some sense. But the absolute values are different. In the first case, it's 0.3 and 0.01. In the second case, it's 3 and 0.1. In the second case, the update is much slower. You showed three examples, and after three examples, it's still a coin flip. Now, when we talk about the emergence of in-context learning with very large networks, what is happening is the parameter count increases, the individual values of those parameters goes down there, and there's a lot more training data. So those values are distributed across much smaller numbers or much larger numbers, so the individual values are small. So even if you had smaller models and you had a large enough context size, then eventually you could have flipped this probability by showing it enough examples. But people did not observe it in smaller models because the context size was not large enough. So the probabilities were not flipping. So they're in some sense more rigid. Whereas these larger models are more sort of amenable to learn new things. Because their parameter count is large, the individual values of the Dirichlet parameters is small. So they change more rapidly. So again, it's consistent with what we observe, this process. It may not be the actual process, but this is consistent with one. So the interpretation of alpha and beta generalization, as I said, alpha A and beta B directly correspond to the size of the network and training data. So one thing that is important here is the ratio of the size of the network and training data. It should sort of scale in a similar way. If you scale one differently from the other, then this emergent property kind of disappears. So in context learning, emerges in larger networks because fewer examples are needed to move the probabilities via the Bayesian learning. If you have a very large context size, then maybe even with smaller networks, you can move them. But with large networks and small context size, it sort of immediately learns. And the example that I showed was a toy example, beta prior, 2 parameters, 2 labels. But using our sort of representation result, you can extend it to any multinomial distribution. Implications? Well, it seems that some kind of Bayesian switch is getting turned on in these networks that to learn or to develop these optimal predictors. Even during the training process, it's sort of incorporating this Bayesian learning process. We are working to show how. We have some sort of ideas, but we're making progress. But at least these examples show that what it's doing is consistent with Bayesian learning. How and why it's happening? Is it related to backpropagation? And is our transformers the right architecture? Are they in some sense parameter efficient compared to other architectures? We don't know, but that needs to be explored. But this is a way to think about them. Now, embeddings play a key role, especially of continuity of embeddings to multinomial distribution. So what's an example of what I'm trying to say? So, these embeddings are developed as part of the training of the model from the training data. And sometimes these embeddings will contain a world model, sometimes it won't. So for instance, the embedding for the word glove and the embedding for the word love, they should be far apart because they mean very different things, although the spelling is very close, right? So they should be far apart. Similarly, if you take the embedding of Robert F. Kennedy and Robert F. Kennedy Jr., then the world model should inform you that they should be far apart. But is it the right thing to do? Right? If you sort of incorporate that world model for one embedding, does it also make other embeddings with a slight perturbation of the input, the embeddings go far apart? Or if the embeddings stay close, the output multinomial distribution becomes far apart, then all that whole Lipschitz property goes away. So I think we need to think how to design these embeddings, how to train these models, and whether the world model should be incorporated into the training process, or simply we should train them on language, logic, and sort of facts. And let all this extra information, world model or specialized knowledge, come in via the context. And it's sort of a Bayesian learning on that on the spot. This model also explains phenomena like chain of thought. So in what chain of thought reasoning is a very popular way to work with these language models, where you ask this model, you give it a problem, and you ask the models to use chain of thought reasoning. So what these models do is then they break that problem up into simpler steps. And people have shown that if you do that, the accuracy of the result is much higher. And that's like, when we prove a theorem, we break the theorem into smaller steps. Those smaller steps have been proven elsewhere. We know how to prove those smaller steps. So then it becomes easier to prove a theorem because those smaller steps are plug and play from elsewhere. So those smaller steps, probably the model has been trained on elsewhere. But if we ask it to solve it directly without breaking it down into smaller steps, maybe that whole problem it has not seen earlier. But when you break it down into smaller steps, it has probably seen something like that earlier. It can generate those embeddings close to that and then update them based on what your actual problem is. Yeah.
The longer the answer, there is a probability that somewhere along the way, with interval probability token, they merge. If you ask me for a shorter answer, then there is a smaller chance of that happening.
No, but when you, sorry, yeah, the question is maybe the model is brittle, and if you ask for a shorter answer, it will not hit a low probability token. But if you get a longer answer, you'll hit a low probability token. Actually, the answer that you generate becomes part of the prompt itself, because every token that you generate gets appended and the embedding of that appended thing goes into the network again. So when you ask it to break it down to smaller steps, your answer is actually becoming longer. But what is happening is the multinomial distribution that is generated, it's more confident in that. In our paper, we have a result which looks at the entropy of the generated multinomial distribution. And using some results from majorization, we show that if you pick the next token in a certain way where the entropy reduces of the next token generated, that means the model is becoming more confident because it has only a few tokens with higher probability and it's becoming more confident. Whereas if you pick the next token where the entropy is high, then it can go off in lots of different directions. So when you ask the model to break it down into smaller steps, then what happens is it has seen those smaller steps earlier. So then the embeddings that are generated, it's confident, okay, I've seen this, my distribution is going to be peaked. Its entropy is going to be low. So it doesn't make it brittle, it makes it more resilient, in fact. Did that answer your question? Okay, sure. Okay, so that ends the talk. Right on time, I guess. Okay. Yeah.
Thank you. So let me just say, we have time for questions, but if people need to leave, feel free, but otherwise we can have several questions.
Sure. Yeah.
So, thank you also. If the model that you're presenting is, let's say, valid and correct, isn't this kind of like damning the dagger in heart for being able to overcome hallucination as long as we use next prediction or as like our training objective in some of these models? Because, like, let's consider a very simple example. Like, let's say that you ask the reigning World Series champion is like, if you train on historical data, then there's going to be some like a multinomial distribution over, all the World Series champions, and of course there'll be a different distribution of training data of how many times people have asked this question in what years. But the bottom line is like you can never really get the model to learn to like attend to who the most current champion is.
Yeah.
So like effectively, transformer, Mamba, like architecture, it doesn't matter as long as the next token prediction is your learning objective. Like you will never overcome this hallucination.
No. So the answer to that is don't use that. Again, go back to my example of helpful but with early onset dementia. Give it the context. So make your LLM based on the question rating world champion is, make, first step of the LLM, interpret what rating means. Query some other database which will tell you what rating is and have the results. Send that to the LLM and ask it to then process and give it the answer. Basic foundational model, no. You'll always run into this problem of going off.
I mean, any relevant statements are different.
Yeah.
Have to write them in absolute terms. Like it's raining, it's up to the years.
Yeah. So you have to give the right sort of trusted data into the context and then only generate the answer.
If you think this model explains why there are emergent capabilities that will also predict the scaling limits of it?
So the question is, does the model also predict the scaling limits? So what we actually show is, yeah, in some sense, yes, it does predict the scaling limits. But the answer is a little bit more subtle. You have to look at the ratio of the parameter count versus the training data and the context length. The context length is important because that's what's sort of giving you the Bayesian update. How much update can you do? And is that update enough to make your model learn? Did that?
In theory, you should be able to, if I give you like the high parameter count.
Yeah. Yeah, it's like for this, the toy example, we showed it, and we can extend that to, a generic model with parameter counts and what it's been trained on. and what the limits are, yeah. Yeah.
On one of your early slides, you used an example like 2 plus 2 equals 4 is higher probability than 2 plus 2 equals 5. It's seen 2 plus 2 equals 4 more often.
Yeah.
If you give me any number, I can come up with a bigger number. So some equation that has never been in the training data before. And I can't expect, right, it's not going to learn how to add. It's not doing the procedural thinking of how you get to 4 from 2 and 2. It just has seen it before. One trick that I've seen ChatGPT do, if I give it something like 2 plus 2, is it'll write some Python code,
Yeah.
like an algorithm. Is that a general solution? Like
It is because ChatGPT doesn't understand numbers,
right.
But it'll understand, okay, now I need to call somebody who knows how to deal with it, right? If you ask it to generate random numbers, people have shown that it'll generate 42 with a much higher probability than other numbers, Hitchhiker's Guide, right? So, so yeah, it doesn't know what these numbers are, but it can recognize, okay, now I need a calculator. Let me bring Python code or bring a calculator. Yeah.
Does that mean the call generator that it almost like it's like given this sort of prompt that shoots the action.
So the question is, follow up to the previous question, that is the call to a Python interpreter a new token? Yeah. You train the model that if you see this sequence of tokens, then the next token is the token corresponding to call Python. ChatGPT, yeah. You train it to behave in that way, yeah.
Theory, if it's such a good Bayesian learner, like you can teach it the rules of arithmetic and all of that context.
Well, yeah, but then it has to recognize the numbers. Right now, it just sees embeddings.
But it probably, like, I mean, numbers might be a different part of its embedding space than words
Yeah.
in English. It's like,
But I have to preserve the same.
Yeah, sure. So that can be tried. That take a blank model, teach it mathematics, teach it algebra, teach it arithmetic.
yeah, like one also an example also that I found really surprising is I tried playing chess with GPT-4 and it seems to play a legal game. Like it doesn't make an illegal move.
Yeah.
Which is I found it extremely surprising, because there's no way you've seen all games.
You've not seen all games, but but it has been trained on several games. So it has seen what the legal moves are. So those are high probability. You probably have not hit that low probability event. Yeah.
Maybe. But yeah, I played a pretty long game. It's not good, but it seems to know the game.
Yeah.
Yeah, one of the problems of LLMs is explainability.
Yeah.
Or explainability. But people seem to feel like Bayesian Bayesian systems are more explainable. So would there be any prospect of using stuff like this to, I don't know, kind of file some kind of response into
So the question is, one of the problems of LLMs is explainability, but Bayesian systems are more explainable. And is there hope that with this kind of a model, they will become more explainable? Yes. We hope. That's why we're going with this model. That's the answer you expect me to give. But yeah. I mean, intuitively, it makes a lot more sense. It at least explains what we have been observing. So, yeah. Yeah.
Does it understand rhymes?
Does it?
For example, COUGH and QUAFF rhyme, but they're completely different in terms of their structure.
So
usage.
Unless it has seen examples of poems where they have been used, it won't. But if it has seen examples, maybe it will. The question is, does it
Insist on it in context.
No, you will say, construct a poem, and it might come up with a poem where it'll make.
But if you tell it that those two words rhyme with prompt, it will
Yeah, yeah, it is learned, right? Yeah. One more.
In this kind of matrix, I feel like this is a giant vision. I like try to learn the transition matrix. I have.
So the question is, does it have any connections to reinforcement learning? I don't think so, but there may be. At least it's not immediately obvious to me. Okay.
Well, thank you, Vishal.
Thank you.
All right, we're ending the Zoom here. So